Welcome to this explainer. Look, we hear about AI models, complex algorithms, and massive neural networks all the time, right? But today, we're unpacking the actual physical reality behind this massive AI boom we're living through. We're exploring Supermicro's data center building block solutions because the sheer physical infrastructure required to run all this AI is absolutely fascinating, and it is evolving at breakneck speed. So that brings us to a pretty massive question. How do you physically build the AI revolution without, literally melting down? To pull off the insanely complex building process for massive AI clusters, we're talking 256 system node setups, we have to start looking at data centers differently. Not as giant monolithic rooms, but as high-tech, highly scalable Lego blocks. By breaking this massive task into smaller, scalable units, the impossible suddenly becomes possible. Ultimately, our destination here is a massive, globally scaled data center, defined by an intricate web of cooling systems and endless server racks. But for this explainer, we aren't just going to jump straight to the big picture. We're going to build this up, step by step, from the absolute smallest individual component all the way to this massive macro view. Here is our blueprint for today. We're taking a micro to macro journey. First, AI compute and storage. Second, mastering in-rack cooling. Third, scaling to the site. Fourth, managing the supercloud. And finally, global deployment and support.
Section 1. AI compute and storage, the foundation of the AI cluster. Let's dive right into the foundational scalable units where everything starts.
Starting right at the micro level, we've got a really diverse portfolio of density-optimized systems. These range from standard one-use server sizes all the way up to massive 10-unit chassis. They integrate the absolute latest tech from industry giants like NVIDIA, AMD, and Intel. And they're explicitly designed to handle the most data-intensive workloads you can imagine, paired with petascale and object storage servers, just to provide the massive throughput required to feed data-hungry AI. But here's the catch, right? When you pack that much sheer computational power into such a tight space, the heat generation is just unbelievable. Traditional air cooling, it simply cannot keep up anymore. That's exactly why Supermicro utilizes direct-to-chip liquid cooling, or DLC. These are specially designed cold plates that sit directly on top of your CPUs, GPUs, memory modules, and even power supplies. They're capturing that heat right at the very source of the computation with extremely low thermal resistance. When you get up close, you can see these physical cold plates bolting directly onto the components. You've got this intricate hosing delivering specialized, optimized coolant right over the silicon. This is literally the physical barrier preventing these incredibly powerful systems from overheating and failing under the intense, continuous demands of AI processing. Moving on to Section 2, Mastering in-rack cooling, managing heat at the rack level. We've cooled the chips, now let's scale it up. To cool an entire rack of these dense servers, Supermicro uses cooling distribution manifolds, or CDMs, which are often mounted vertically to save precious rack space. You can really think of these as the primary arteries and veins of the server rack. They distribute the chilled liquid coolant to each individual server, and then they collect and return the hot liquid that just absorbed all that heat from the cold plates. Now, liquid obviously doesn't move on its own. Pumping that coolant through the manifold requires a very serious piece of hardware, the in-rack coolant distribution unit, or CDU. This unit is an absolute workhorse. It handles an impressive 250 kilowatts of cooling capacity all on its own. And since AI workloads just cannot afford to go offline, these CDUs feature redundant pumps, either 2N or N+1 setups, meaning there is always a backup ready to go. They even include touchscreens and web interfaces so operators can monitor the fluid dynamics in real time. When you actually combine all these elements, the dense compute nodes packed with heavy metal heat sinks, the liquid, the metal manifolds, and the high-efficiency 5500-watt power shelves needed to power it all, the physical weight is astounding. We're talking about a static load capacity of 2,500 kilograms per rack. To put that into perspective, that is literally the weight of a large SUV, meticulously engineered into a single server rack. Which brings us to Section 3, Scaling to the Site, Megascale Infrastructure. Once you've mastered the single rack, you just multiply those foundational blocks. But as we zoom out from a single rack to an entire row of servers, the cooling requirements scale exponentially. Enter the in-row coolant distribution unit. This single unit steps up the game dramatically, supporting a staggering cooling capacity of up to 1.8 megawatts. It prevents any interruption to the cooling flow across an entire row of massive AI compute power. Depending on the physical facility you're dealing with, there's a lot of flexibility at this macro scale. On one hand, you can use liquid-to-air sidecars that give you up to 200 kilowatts of cooling without even needing facility water connections. But on the other end of the spectrum, for true megasites, they utilize massive closed-loop water cooling towers. These scale from 1 megawatt all the way up to 50 megawatts or more, maximizing energy efficiency while dissipating unbelievable amounts of heat into the atmosphere. But all this incredible physical scale, rows upon rows of 2,500 kilogram racks, has to act as a single cohesive brain. That's tied together with optimized site-scale networking cabling. It's not just about plugging in wires, it's about traffic engineering. This comprehensive cabling design reduces the time to online, cuts material costs, and most importantly, ensures bottleneck-free data flow across thousands and thousands of processing nodes. Section 4. Managing the supercloud. End-to-end software control. Let's face it, a massive physical site, no matter how beautifully cabled and liquid-cooled, is essentially useless without a brain to run it. To manage this staggering amount of global-scale hardware, Supermicro provides an end-to-end software suite known as SuperCloud. Through this unified dashboard, physical reality meets digital control, offering complete infrastructure management and deployment automation. The SuperCloud suite is broken down into 3 main pillars. First is the Automation Center, which handles the incredibly tedious task of OS and firmware provisioning across thousands of nodes. Second is the SuperCloud Composer, which is basically the watchful eye over your hardware, providing unified rack scale management and, crucially, advanced leak detection for all those liquid cooling systems. And finally, the SuperCloud Director gives you multi-tenant AI cloud control, letting you manage bare metal servers and networks securely. And finally, Section 5, Global Deployment and Support, from concept to reality. So we have the highly engineered hardware and the software brain. How do we actually deploy this out in the real world? Supermicro breaks this massive undertaking into a streamlined 4-step journey. Step 1 is meticulous planning, topology, floor plans, cabling. Step 2 is rigorous validation at both the rack and cluster level. Step 3 is on-site deployment, featuring white glove delivery, where they handle the heavy racking and stacking. And Step 4 is ongoing on-site support, where they offer an incredible 4-hour on-site response time to make sure these critical systems never stay down. All of this is backed by a massive footprint, highlighted by a 1.5 million square foot green computing park in San Jose, California. By actually owning this end-to-end process, from the copper cold plate to the software dashboard to the delivery track, they are able to provide massive economies of scale and accelerated support for AI and cloud computing customers literally across the globe. So as we've seen in this explainer, scaling from a single liquid-cooled chip all the way up to a staggering 50 megawatt data center site is entirely possible when you have the right building blocks. But it leaves us with one final essential thought to consider. As AI demands continue to just skyrocket and models grow exponentially more complex, how will your infrastructure evolve to meet tomorrow's reality? Thank you for joining me on this explainer, and keep building the future.